Now that we're getting used to molarity and dealing with solutions, it's time that we start talking about another class of compounds than what we've been discussing. And it's one that you've also heard of before, and I'm going to refer to it a couple of times. The big class is called electrolytes. And electrolytes are materials that dissolve in water and release ions. So you might be asking yourself, well, we just talked about ionic compounds, and some of these obviously were electrolytes. Why didn't we mention it? Well, electrolytes are a bigger class. Ionic compounds are one type of electrolyte. And these ones, of course, only the soluble ones are the ones that are electrolytes. If they are not soluble, then they don't dissolve at all. So we have another class of compounds that fits under the greater heading as well of electrolytes, and that is acids. And we're going to spend some time talking about acids. We're going to use a specific definition of acid, and there are several. We are going to be using the one that's called the Bronsted-Lowry definition. And the Bronsted-Lowry definition of an acid is any compound that donates an H plus to the solution when it's dissolved. So let's look at a couple of examples of these. Some examples of acids you've probably heard of. HCl is called hydrochloric acid. And HNO3 is called nitric acid. Another familiar one is H2SO4, which is sulfuric acid. And these are three examples of strong acids in particular. So when we talk about electrolytes and acids, we can talk about strong electrolytes and we can talk about weak electrolytes. We can also talk about strong acids and weak acids. Strong electrolytes and strong acids, these dissociate completely in solution, and weak acids and weak electrolytes dissociate incompletely. Anything from just a little to a decent amount, and that's pretty variable. So these three acids that I just mentioned, HCl, HNO3, and H2SO4, these are all strong acids, so that means that when they get in solution, they dissociate completely. So we would write that HCl aqueous is really H plus and Cl minus, and HNO3 would really be H plus aqueous and NO3 minus aqueous. And H2SO4 would be two H's and SO4 2 minus. So what you might notice right here is that these anions, chloride, nitrate, and sulfate, these are all familiar from when we had conversations about our ionic compounds. And many of the anions that we've already studied in ionic compounds do bind with H plus to form an acid. Now, there are relatively limited numbers of strong acids, but there are a lot of different weak acids. So the main strong acids, there's some argument about whether there's 6 or 7, but we'll just go with 6. We have hydrochloric acid, hydrobromic acid, and hydroiodic acid. So these are all H plus with a halogen, And then we also have HClO4, HNO3, and H2SO4. So these three are H plus a specific polyatomic anion. And I should still say that's still an anion. Okay, so these are the 6 strong acids that you are responsible for knowing. Now, I did mention weak acids, and we're going to get into those a little bit more later, so I'm not going to spend too much time on them right now. But one example of a weak acid would be acetic acid. So let's look at that name here. Acetic sounds a little bit like acetate, and in fact, that's exactly what this is. This is the protonated form of the acetate ion. So this would be able to dissociate into acetate ion and H+. So what did I just say here? I said protonated. This is one of the terms you hear a lot when we talk about acids. So let's pull this apart a little bit. Proton, right? We know that this is the one of our subatomic particles. So why did I just call this protonated? Well, let's look at what's going on right here. H+. Remember what H is? We said that hydrogen 1, which is our most common form here, the subatomic particles here would be 1 proton and 1 electron to make 1 atom of H+, right? So in the nucleus, I have 1 proton and no neutrons. And then outside the nucleus, I have 1 electron. But wait a minute. If I now have H+ here, H+ means that I lost the electron. And that means that the only thing that's left here is a proton. So an H+ is the same thing as a proton. And so when we call an acid protonated, we're saying that it has the H+ so that it is in the form of the full compound, not the dissociated form. Okay? So this is the protonated form of the acid. And the same thing would be true. HCl is the protonated form of hydrochloric acid. So part of our job right now is to get you familiar with some of the vocabulary of how we talk about chemicals. And this is one of those ones that is really common. We probably won't use it as much this year as you will next year when you take organic chemistry, but it is part of our terminology, and so I will probably throw it out there sometimes, even when I'm not thinking about it. So I wanted to make sure that you heard the term and that you were familiar with the term. Okay, so let's take a look at what makes something an acid. So how can we recognize an acid? So you probably can notice that an acid is going to be anything that has 1 or more H+ and an anion. And so usually this anion is usually non-metal, but we have a couple of metal containing anions, but most commonly we will see an anion that contains some nonmetals, and we also have to have the presence of at least 1 H+. So if we think about some of our anions, like cyanide ion or chlorate ion or nitrite, since we've already talked about nitrate, or sulfite, since we've already talked about sulfate, for example. So yeah, if we add a proton to this, we absolutely get an acid. So this would be hydrogen cyanide or hydrocyanic acid. We can get HClO3. So that would be chloric acid. Hydrogen chlorate will be less confusing here. So this HNO2, yep, hydrogen nitrite, 2 H pluses, H2SO3, absolutely. All of these are acids. All of these are weak acids, except for this one, which we already, this one is borderline. But all these other ones are weak acids. So if you add H plus and an anion, you're generally going to be able to make some kind of an acid. And we'll get more experience with dealing with acids pretty soon as we keep going. So when we look at acids, acids are generally very reactive. The H plus that they donate into the solution is what's doing the majority of the reacting. And so usually the stronger the acid, the more active it is in a chemical reaction. And acids don't just have one kind of thing that they can do, but one of the most common kind of acids or acid reaction is a reaction between acids and bases. And we already saw what the Bronsted-Lowry definition of the acid was. The Bronsted-Lowry definition of a base well, the acid was donating the H plus. The base is accepting the H plus. And just like we have strong acids and weak acids, we have strong bases and weak bases. Right now, we're going to focus just on the strong bases. And the strong bases are super easy to recognize because the strong bases all have OH minus as their anion. But they also have to be soluble, or mostly soluble. So we know that OH minus is usually an insoluble anion, so that means that we have a relatively limited list of things that count as strong bases. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide, so those are all alkali metals for the anion or for the cation. And then we have barium hydroxide, strontium hydroxide, and calcium hydroxide. And these are all three alkaline earth metals for the cation. So they're all close to each other on the periodic table. It should make it pretty easy for us to remember these six. And of course, we also know our solubility rules. And so if you can remember your solubility rules for OH minus, then you're all set. So let's look at a reaction between a strong acid and a strong base. So pick your favorite strong acid. I'm just going to use nitric acid, HNO3, which is soluble, and we'll go with sodium hydroxide, a really common strong base. So we know that both of these will dissolve in solution, and so we might want to start by talking actually about the total ionic equation already. So we know that this acid will separate into H plus and NO3 minus. And we know that sodium hydroxide is also soluble because sodium is always soluble. And so we have Na plus and OH minus. So this looks very much like the ionic reactions we've already been doing. And just like we did before, we're going to swap the cation and anion pairs here. So our sodium and our nitrate are going to go together, and our H plus and our OH minus are going to go together. So we're going to get sodium nitrate. And what happens if we have two H's and an O? Yeah, that just makes water. Okay? So when we look at this from a total ionic equation standpoint, we're going to separate the soluble ionic compounds. That's sodium nitrate. But we already said with precipitation reactions that if we have a solid, or if we have a pure liquid, or anything that is not a soluble ionic compound like this one, we're just going to leave it alone. So this is our complete ionic equation for this reaction between a strong acid and a strong base. And I want to draw your attention to another thing here too. Here we have water, and then this is just an ionic compound, right? This is a soluble ionic compound. Plus water. And this soluble ionic compound, it actually doesn't have to be soluble. But when we have a generic ionic compound that doesn't have any acidic or any basic characteristics, we just call this salt. Salt is a generic term, even though we use it very specifically for table salt. Salt is actually a generic term for an ionic compound. Okay, so let's take a look at this. We've got this generic neutralization reaction, and that's exactly what we just did. This is a neutralization reaction, and it was a strong acid plus a strong base. It made salt, a soluble ionic compound, and water. And now we wrote out the total ionic equation, so let's look at the net ionic equation. What are our spectator ions? Let's see, it's getting a little crowded here, but I think we can do it. So here's sodium, and here's sodium. That's just hanging out on both sides. And I see nitrate here and nitrate. So these are our spectator ions. Now what's left over? We have H plus OH minus makes water. And this will always be the net ionic equation for a neutralization reaction. So if you have done the total ionic equation and the net ionic equation, and then this is what you get, you know you have done a neutralization reaction. Okay? So take a moment here and let's predict the products for a couple more reactions. So let's practice what we just did. Let's take H2SO4 and potassium hydroxide. So predict the products and balance the equation, and I'll put up another one too. So what you have to do when you predict the products, or when you look at a reaction like this, is you need to look at what is in my reaction. What kinds of materials are in my reaction? What kind of reaction am I looking at? Is this going to be a precipitation reaction? Is this going to be a combustion reaction? Is this going to be an acid-base reaction? We now have 3 kinds of reactions that we can pay attention to. So we need to look at what the clues are. Do I have an acid? Yes. Do I have a base? Yes. Okay, it's probably going to be a neutralization reaction. Do I have a fuel? Do I have oxygen? If so, then it would be a combustion reaction. Do I have 2 soluble ionic compounds making an insoluble compound? Then it's a precipitation reaction. So we're just going to go ahead and predict these products, and just a little hint, these are probably acid-base reactions because that's what section we're in. So pause the video and do this. And if you want extra practice, you can also write out the total ionic equations and the net ionic equations. All right, coming back together now. Hopefully you noticed that stoichiometrically we would end up having K2SO4 to react with our sulfate ion here, plus 2 waters. And so this would require a 2 right here for balancing. And as far as phases go, these are both soluble. This is soluble, that's the salt for this reaction, and then this would be liquid. Water is going to usually be liquid phase, unless it's a combustion reaction, in which case it's really hot and it would be a gas, but we're not worried about that right now. So here, once again, we have a 2-to-1 relationship because we're going to make calcium chloride, which is soluble, and 2 waters again. And if you tried out the total ionic and the net ionic, hopefully you ended up with a net ionic equation that looks like this one, and so you know that you've done it right. So we've done quite a bit of vocabulary in this video, but I want to do just a little bit more. So I talked about the fact that we have these acids and we call them protonated if the H plus is attached. The other thing that we will talk about here is a classification for the acid in general. We will see that these are protic acids. And what this means is that this acid is acting like an acid because it donates a proton. So this type of acid donates H plus. Now you're probably going to say, wait a minute, back at the beginning of the video, didn't you say that the whole definition of this acid was that it donates H plus in solution? Yes, exactly. So this fact that we are classifying some acids as protic does imply that some kinds of acids don't do this, that they do something else. And we're not going to get into what they do right now, but you will see this term, and so I want you to understand that that's what this means. That there are other kinds of acids, we're not going to worry about them. But the way that this might come up is that when we look at an acid like H2SO4, we can see that it has 2 H's, and so this would be called a polyprotic acid, because it has more than 1 H plus that it can donate into a solution. And so, as you can see up here, when you have a polyprotic acid, they react with that base in a stoichiometric way so that they can neutralize or, dissociate all of the protons that are in solution. The other thing that you will hear when we're talking about acids is that there are some materials that are called amphiprotic. And an amphiprotic material means that it can act like an acid or a base. So our main example of this is water. When we have water in solution, one of these waters could donate an H plus and dissociate like this, and then the other water can accept it, making H3O plus OH minus. And so this is an example of an amphiprotic behavior. There are not very many out there, so this is the main one that we talk about. In fact, in solution, we said that H plus shows up and is donated by an acid. H plus really is H3O+ in solution. These little protons do not hang out on their own. As soon as they get into solution, they find a water molecule to hang out with, and they make this hydronium ion is what it's called. All right, so you've had a lot of vocabulary in this video. We've defined acids and bases. We've talked about protic things. We've talked about polyprotic, amphiprotic. There's a lot of content here, and so I'm not going to talk about reactions other than the neutralization reaction in this video, but the short version is that you can do any calculations that we've been doing with ionic compounds, things with molarity and stuff. You can do that with acids and bases as well. So in the next video on stoichiometry, we'll have a few examples of those just to make sure everybody is solid with them.